Okay, here we're going to actually show that for a system of objects, they will act as if all of their mass is concentrated at the center of mass. We're going to do that by considering a collection of three objects right here. We will take that each object will have an external force acting on it. In addition, each object will exert forces on the other two objects. And then what we're going to do is take and apply Newton's second law, F equals ma, to each one of the objects in turn. So for an example, we'll take the first object right here. We're going to add up all the forces acting on object number one. That will include this one external force, the force exerted by object 2, and the force exerted by object 3. Add all of those up, and that's the net force acting on the first object. That will equal its mass times its acceleration. We do the exact same thing for the second and third objects, and we then have three equations that describe the motions of the three different objects. However, notice, each one of these internal forces will come as part of a pair. Here is the force that object 2 exerts on object 1, and here is the force that object 1 exerts back on object 2. These two constitute an action-reaction pair and will necessarily be equal and opposite, as will the force that object 3 exerts on object 1 and the force that object 1 exerts on object 3, and the force that object 3 exerts on 2 and 2 exerts on 3. Those are all action-reaction pairs. So then what we're going to do is add all of these equations up. When we do that, all of these internal pairs are going to cancel out, and the only thing that's going to remain on this side of the equation is just the sum of the three external forces. So when we add them all up, we will have that the sum of the three forces will equal the sum of the masses times the respective accelerations. We haven't quite finished yet, but what if we take the center of mass of the system and take its derivative? Well, the center of mass of the system is just the sum of the masses times the positions divided by the total mass. So if we take the derivative, we end up with the velocity of the center of mass will equal the mass of the first object times its velocity plus the mass of the second times its velocity, etc. And all of that divided by the total mass. Then if we take the derivative of that, we then get the acceleration of the center of mass, which will be the weighted average of the accelerations divided by the total mass. Take and multiply both sides of the equation by the total mass, we then get what we have over here is equal to the total mass times the acceleration of the center of mass. Combining that all together, we get the net force, which is the sum of the three external forces, equals the total mass times the acceleration of the center of mass. Or we get exactly what we wanted to show, that this collection of objects acts as if all of the mass is concentrated at the center of mass, and that center of mass, that point, is what accelerates as a consequence of the net force acting on it. Or the net force is the total mass times the acceleration of the center of mass. This is why the center of mass is the point that we follow when we have either collection of objects or an extended object in motion. Now, some of the implications of this are the following. Regardless of what the different parts of a system does, which could include the system exploding and flying apart, the center of mass will continue to move regardless of what happens. It'll move only in response to the external forces. So if we have an object exploding, the center of mass will continue to move as if nothing had happened. If the net force is 0, then the motion of the center of mass will not change, which means if it was moving at a constant velocity, it will continue to move at a constant velocity. Namely, that's what the center of mass will do. Pieces may do other things, but the center of mass will obey the law of inertia. If the center of mass is at rest, then it will always remain at rest. Different pieces may fly off in different directions, but the center of mass will remain at rest. Unless, of course, there's a net external force acting on it. Now, to see how this works, we're going to consider a few examples. And I want you to answer each one of these examples in the Google form attached to this video. The first example, we're going to have a penguin. We're going to be on a sled on some ice. Both the penguin and the sled are initially at rest. We'll take the penguin and the sled as having the same mass. For simplicity, we're going to take the sled as having a length L, and it'll be of uniform density. we'll measure all of our distance from the left end of the sled, which is where the penguin starts out. So first I want you to figure out where is the sled's center of mass in terms of L and M, and then where is the system's center of mass? And the system will be the sled and the penguin. Then what will happen is the penguin will waddle from one end of the sled to the other end of the sled. I want to know, how does the system's center of mass move while this happens? And how far in what direction does the sled's center of mass move? So answer those on the Google form. Okay, in the second example, we're going to have a man of mass M on a rope that's attached to a balloon. Initially, the balloon and the man will be at rest. The man has a mass little m, the balloon, along with its occupant, has a mass of capital M. And again, they'll start at rest. This man then climbs up the ladder, moving with a velocity v, where v is measured with respect to the ladder. What I want you to figure out is, in what direction and with what speed does the balloon move with respect to the ground while the man is climbing up the ladder? Then the man gets off the ladder, climbs in this little basket right here. He is now at rest with respect to the balloon. Now, how is the balloon moving relative to the ground? So in both cases, we want to know the speed of the balloon and its direction of motion relative to the ground. So again, put your answers in the Google form that's attached. In the last case, we're going to have a shell that's fired up at a 60-degree angle with a speed of 20 meters per second in this arc. However, at the top of its trajectory right here, the shell will explode. Part of the shell will basically fall straight down. The other part of the shell will continue moving forward. What I want to know is, first, where would the shell have landed if it had not exploded? And then secondly, where does the center of mass of the shell land after the explosion? And finally, where does this second piece land after the explosion? In all cases, measure the distances relative to where the shell was fired from. Again, enter those onto the Google form attached.